Department, and some of you are in violation of the policy. We have cameras here that are taking a photo record. Anyone without a Hawaiian shirt is losing 10 points. Okay, I'm kidding. Last day we talked about this magnet detector. We found that anytime we change the number of magnetic field lines that go through a loop, we generated a current. We call it an induced current, meaning it's invisible. We can't see the battery that causes it. And we could use that as a magnet detector to detect when a magnet goes through that coil. Well, what we wanted a metal detector. And so what we did is we put a second coil up there. Now we could have just magnetized the piece of steel with a bar magnet, and that would have worked. But instead we used a coil. We hooked that coil to a battery, and then when the steel went through the coil, it got magnetized. It became electromagnet, and then that tripped our detector. Okay? And we decided right at the end of class that if we were to walk really, really slow with this gun, we could get through this detector, but not the one down at the airport. Okay? Now, as a review, this idea of magnetic flux is not so scary as it seems. Magnetic flux is just the number of field lines that go through the loop. And we're going to treat this as a vector. And the direction of that vector would be the same direction as the field lines go through the center of the loop. Now, it becomes useful, helpful, if we distinguish between two different flavors of field line, of flux. We're going to distinguish between external flux, or external field lines, and those are field lines caused by everything else except for the coil. Okay? So when I bring this bar magnet up, the external field lines would be due to the bar magnet. Now when I bring this bar magnet up and change the external field lines through that coil, I get this induced, can't see the battery that's causing it, current that creates its own field lines. Those field lines we call induced flux or induced field lines. And we'll always be keeping those two separate from each other in today's lecture. Okay? Now, the hope is that that tutorial was enough to just make Lenz's law obvious to you. My experience has been that you're just on the edge, you're just on the verge of understanding, and we need to tip you over into that happy valley. And so that's my goal today, is to get you to where you're feeling all really warm and fuzzy about this. Now there's Faraday's law. On the left-hand side, we have that invisible battery that drives the induced current around the coil. That battery, the size of it, depends on how quickly we change the external field lines through the loop. And N is the number of loops in the coil. Now, it's important to note that this EMF, this battery, is set up whenever I change field lines through a loop. If I had I didn't bring one. But if I had a plastic, I got an idea. There is a loop of human flesh, fat human flesh, okay? If I change the number of field lines through that loop, Faraday's law says that an invisible battery is set up around that loop. And that's true whether this loop is made out of human flesh or out of copper. I get exactly the same battery set up if I change the number of field lines the same way. The difference is, when I set up the battery around my fingers, my resistance in my hand is so high that electrons don't start flowing. But if instead I had a copper ring and I did that, the same battery would be set up, but now the electrons would be free to flow and I would get the induced current. So I get the induced battery one way or the other. Whether I've got skin, or this could be a glass ring, or a plastic ring, or a wooden ring. But if it's a metal ring, that battery is going to drive a current. And that current we call induced current. Now, we've come here today to talk about this part, the minus sign. That minus sign has a name. It is called Lenz's law. And it's one of the most important minus signs in physics. Okay? What it means, in a nutshell, is fight. It tells us that this induced current is always going to flow in a direction to fight any change in external flux through the ring. Copper rings don't like change. They fight change. And Lenz's law tells us how it happens. Okay? Now, I have a demo here that I hope someday will make me rich. Filthy rich. Right now I'm just filthy, but this is going to make me filthy rich. I have here a copper pipe. And tell me, Pat, anything in that copper other than my eyeball?
Yeah.
Just my eyeball, okay? There's just nothing in there. Now, I have a steel plug, and steel does not stick to copper. Steel does not stick to steel. I'll find that. I also have a very strong magnet that does stick to steel. But as it turns out, magnets don't stick to copper. Copper is a non-magnetic material, so it just falls off the copper, okay? Just like the steel. Now, what I'm going to do is race these two through that pipe. Now, let's start with the steel. And I'm going to time how long it takes to get through this pipe. Ready, set, go. Let's time it in seconds. Ready, set, go. 1/1000. Ready, set, go. 1/1000. Exactly 1 second. Now, people, that was the steel. Copper does not stick to magnet. Magnet does not stick to copper. How long will it take this magnet to get through the copper pipe? Talk to your neighbor. Talk to your neighbor. Am I too close, my friend?
Oh.
Okay. Magnets do not stick to copper, so the answer is 1 second. It takes exactly 1 second for this to get through here. Watch. Ready, set, go. 1/1000. 1 second. Okay. Now I need some help. I need a witness. Would you stand up and look down this while I drop the... Okay. Is it stuck, sir?
There's something in there.
Okay. Is it stuck on the side?
Nope.
Is it floating?
Yes.
Is it the coolest thing you've ever seen?
Second coolest.
Oh. That's intriguing. Okay. As a geek, it is fully the coolest thing I've ever seen. Okay. Now, it's just floating down there. It's just floating down there. And it just kind of gradually moves its way down. It never gets stuck. It just floats its way down and then out. Now, here's here's the catch. Magnets don't stick to copper, but whenever I bring a magnet near a copper ring, I generate a current. As this thing is dropping down this pipe, it's getting closer to the bottom of the pipe. Well, the bottom of the pipe is a copper ring. And if I drop that magnet, the real magnet, with the north pole down, that's going to induce a current in the bottom of the pipe, and that current represents an electromagnet. And that current's going to be set up in a direction such that the north pole of that little electromagnet is up, fighting the motion. North pole against the north pole. Not only that, but whenever I take a magnet and pull it away from a copper loop, that generates a current. Okay? And that's what happens when I leave the top of the pipe. I generate an induced current. In this case, that induced current is going to be around this way, so that the north pole of the electromagnet is down. I've got a north pole saying to the south pole, don't leave me, come back, come back.
It's Jerry.
What is that?
It's Jerry.
Oh, okay.
Would a stronger gravitational field make it harder to get through?
Stronger gravitational field would actually make it harder to get through. And that's because it's the gravitational energy that is being turned into this current. If I just drop something without the copper pipe, I get potential energy, gravitational energy, being turned into kinetic energy. It speeds up. When I drop this down the copper pipe, suddenly I have these currents generated. That's energy. That's energy. That has to come from somewhere. And so instead of the gravitational energy turning into kinetic, it turns into this current. Now, those currents have to be in the direction I indicated. Otherwise, we would violate our conservation of energy. Let's imagine that we lived on a planet in a different universe where the laws of physics were completely backwards. It's the place where Spock has the beard. Okay? Now, in that universe, when I drop this north pole down, the currents are opposite what I've drawn here. What's going to happen to this bar magnet when I drop it down the pipe? It's going to go zipping out the other side. What I have in my hand right now, on that planet, in that universe, would be a bazooka. All I have to do is put this magnet in the back and give it a tap, and poof, it comes out the other side with free energy. Well, that's not where we live. Now, I said I wanted that demo to make me rich. That's because one day I hope to build a tube, not this big around, but as big around as this room and 10 stories tall. And I'm going to have a suit where I'm going to put thousands and thousands of these little magnets on there. And then what? I'm not going to jump in. I'm going to charge each of you $50 to put on the suit and jump in. And you're just going to float and have fun, do flips, and it's going to be worth the $50. Because every morning I'm going to have to pay my brother Kenny to put on the suit and jump the first time. Because what happens if a terrorist comes in the night and cuts a little slice so tiny you can't see it along the side of the pipe? What happens to Kenny? Falls like a rock. He'll do it. Kenny will do anything for money.
When does the magnet flip? Because there's the blues on the top, and then at the bottom, the blues on the bottom.
Oh.
When does it flip?
This one is fighting North Pole against North Pole. This is trying to come towards it, and so the North Pole's saying, don't come here.
I see. Okay.
Whereas that one's saying, don't leave me.
I got you.
That's why they're reversed.
That's not.
Oh, can you fire this down and get it to repel? I never tried that. That's an excellent question. This demo was first developed in India. And then one of our professors here at MSU, Jerry Wheeler, he was visiting India and he saw this demo he brought it back to the United States. Now he and another MSU professor, Larry Kirkpatrick, were the host. They were in charge of the big American Association of Physics Teacher conference for the whole country. All these geeks descended on Bozeman, and it was a geek fest. They showed this demo. They didn't have neodymium magnets because they had not been developed yet, so they used a cow magnet, the type they put in cow bellies to attract the spare metal that they eat. And before the end of the day, Big R, Murdoch's, was completely sold out of cow magnets. And they said, man, we don't know what happened. There were some geeky looking people buying magnets. We're a little worried. That was a very fun conference. Larry Kirkpatrick dressed up in a full gorilla outfit. You remember the monkey drop that we did in 205? They dropped him from the ceiling, from the roof of the field house, down into one of those pits where they pole vault. And in the process, they were shooting him with a cannon. And physicists can have fun when we've got the shirt. Now, okay, we are going to use this idea to develop Lenz's law. This idea that whenever I bring a magnet towards a ring, the coil sets up a current so that it turns into an electromagnet that fights my motion. North pole against the North Pole. When I pull it away, it fights that motion by North Pole against the South Pole. Okay, so let's look at that real quick. We're going to look at two experiments. The first experiment, we're going to take a ring and we are going to drive a North Pole down on that ring. And as I do it, I want you to answer this question. How does the dipole have to be set up in that ring to fight that motion? Would this turn into an electromagnet with a North Pole up or a South Pole up? A North Pole up. Now, which way does induced current have to go around this loop to make that kind of an electromagnet? Right hand rule number 3, it's got to go counterclockwise like that. Now I need you to think about the center of the loop. The center of the loop. And think about the two different flavors of flux, of field lines. Okay? I got the external flux due to the bar magnet. I have the internal flux due to this current that's induced. Now, what direction will the external flux point through that loop? If I've got a North Pole, the field lines come out of the north and then spread. So what direction do they go through that loop? Down. And there aren't very many that get through the loop because I'm so far away. Now the induced current goes around this way, so induced flux or induced field lines are that way. Notice that they're opposite the external flux. That, it turns out, is not important. I just wasted your time. Now, as that North Pole gets closer and closer, the external flux gets bigger and bigger. Okay? Now, one more experiment. This time I'm going to take the North Pole and I'm going to pull it away. Now, this is going to turn into an electromagnet. What am I going to have here up next to the North Pole? Will it be another north or a south? South. A south to fight the motion. And that means that induced current is going to have to flow the other way, clockwise, in order to make this dipole. Okay, it's going to have to go around that way. Again, let's think about the flux at the center of the loop. I've got external flux, that's due to the bar magnet, coming out of the north. My induced flux is caused by this. Notice that the induced flux is in the same direction as the external flux. That is not important at all. Okay? Let's put these side by side. In the case on the left, I start with a little bit of flux down, external flux, and then when the bar magnet gets closer, I have more flux down. The change is what I have to add to this short vector to get a long vector. And that's the plus sign right there. Now notice that the induced flux is opposite that change. That's important. That matters. If we look at the other experiment, we start with a lot of flux down, because I start with the magnet close, and as I pull it away, I have a little bit of flux down. My change vector is what I have to add, there's a plus sign, to this long vector to get a short vector. And sure enough, the induced flux caused by the induced current is opposite that change. That's the piece that's important. This induced flux will always be in the opposite direction of the change in external flux. Always, always, always. As I said, copper loops hate change. They fight change. They fight it with a passion. I think of these copper loops as Republicans. They don't like change. Didn't like Social Security, Medicare, the whole 21st century. However, these are like Republicans in New England. They don't win, they just fight. Okay, these are like New England Republicans. Okay? Have I painted a picture for you? All right. Good. Okay. Now you need to know, Mitt Romney is one of my best friends in the world. I mean, when we were in school, we were his nannies, my wife and I. Whenever they left town, we went into their house and took care of their children. And they are excellent, wonderful, wonderful people. I didn't vote for him. Okay. Now we're going to practice. Okay? I've constructed a coil of wire, a solenoid, if you will. The current goes round and round and round and round and round and round this tube. And then I take the wire at both ends and I solder it together right there. Now, when I bring this south pole near that solenoid, that coil, it's going to induce a current that goes around this coil, either this way or that way. Now, if it goes around this way, up the front, it's going to come down the back and across this wire to the left. If it coils around the other way, down the front, it's going to come down the front and through this wire to the right. My question to you is, which way does induced current flow through that wire there when I bring the south pole close? Let's do this one together, then you're going to do it alone. Let's first of all use the approach where it's got to fight the motion. If I'm bringing a south pole close to this coil is going to become an electromagnet that will fight the motion. Will this pole here be a north or a south? South. A south, okay? Now, in order for that to be a south pole, this has to be a north pole. By right-hand rule number 3, that means the current, induced current, is going up the back and down the front. Up the back, down the front. Up the back, down the front. If it comes down the front, it goes through this wire to the right. Okay? You see how this game is played? Okay. It turns out there's a lot of situations where we don't have relative motion. And so this whole idea of fight the motion isn't going to solve the problem. So let's learn how to solve the problem with Lenz's law. With Lenz's law, I would say, first of all, I would have to distinguish between external and induced flux. By external, I mean flux due to this guy. Anything that's not the coil. Now the flux due to this guy, field lines come out of the north, wrap around and go into the south, but I don't care about it everywhere. I care about it here through the coil. And here through the coil, the field lines are towards the south. And so I would have a flux to the left. It's not a big flux because the magnet's far away. When I bring that bar magnet closer, I get more field lines that are going through the coil to the left. Now, the change is what I have to add to the initial to turn it into the final. I'm trying to make a short vector a long vector. My change is going to be in the same direction. The induced flux fights that change. Okay? In order for induced field lines or flux to go this way, I have to have induced current go up the back, down the front, which means to the right. Okay? To the right. Yes?
So you know the field lines are going left because they're going into the south?
I'm sorry?
Do we know that the field lines are going left because they're going into the south?
Yes. These field lines, the red ones, are the external flux due to this bar magnet. And they always go towards the south or away from a north. That's how we determine the direction of the external flux. You remember that Faraday had those, the ability to see the field lines. And he could see these field lines coming out of the north and spreading out. Okay? And so if I brought a north pole up to this coil, out here, not very many of them are getting through the coil because they spread out. But when I get closer, more of them are getting through the coil. And when I get up here, all of them are getting through the coil. When I pull it away, now I only get maybe 1 or 2 field lines through the coil. Does that make sense? Okay, now you're going to try it on your lonesome. If I pull that north pole away from the coil, will the induced current in this wire flow to the right, to the left, or I don't know. I'm going to give you a chance to vote with your clicker.
It's gonna go up, right? What? If you were paying attention.
Okay, with your clicker. Does it flow to the right, to the left, or I'm confused? Okay, last call. Okay, the answer is to the left. Good job, 87 people. Let's do that together. With this north pole here, field lines due to the bar magnet are going away from the north and spreading out. Because it's close to the coil, I get a lot of field lines that actually make it through the coil. When I pull that magnet away, I don't get as many field lines that make it through the coil. What I care about is the change in external flux. What do I have to add to this long vector to the left to make it a short vector to the left? Well, I got to add something to the right. That's my change in external flux. The induced flux, caused by the induced current, fights that change. And so it would be to the left. In order for induced field lines to go through this loop to the left, induced current has to go up the front and down the back. Up the front, down the back. If it goes down the back, it comes down this wire and to the left, like that. Opposite what we had before. Now, here's an example where there's no relative motion. You cannot possibly solve this problem by fighting the motion. There is no relative motion. So the question is, when I close that switch, for a moment I get an induced current in this coil, and then it goes away. Right when I close the switch, it happens. That induced current will flow to the right or to the left of this wire here with your clicker counting. To the right or the left. Use Lenz's law. Okay. Are we done? Oh, we don't know. We don't know. And more importantly, we don't know that we don't know. Only 2 of us admit to being confused, but obviously more of us are. Okay, let's do it together. When the switch is open, how much external flux do I find over here due to that coil? None. None. And I represent that with a dot. Okay? Now when I close that switch, this is the positive terminal of the battery. That means conventional current flows up the front, down the back, up the front, down the back. What kind of pole does this turn into? A north pole. Okay? So that means that the pole closest to this solenoid is a south pole. That means flux due to that is going to be going towards the south. Now, I'm looking for the change. What do I add to nothing to get something to the left? I have to add something to the left. And it's that change that we will fight. Okay? Now, if that induced flux or field lines is this way, induced current has to go up the back, down the front, up the back, down the front. It'll come down the front and to the right in that wire. By right-hand rule number 3. Okay. Now, there's a mistake in this diagram. Can you tell what it is?
Blue arrow should be the same size as the purple.
Ah, the blue arrow can't be bigger than the change that it's fighting. The induced flux fights a change, but it never wins. Indeed, it has to be smaller than the purple arrow, unless you've got a case where you've got a perfectly conducting coil, a superconducting coil. Okay? Excellent. Good job. Okay. Now, I can leave this switch closed as long as I want, all afternoon. The induced current only shows up for an instant and goes away. But it comes back right when I open the switch. And when I open the switch, I'm going from a lot of external flux to the left, towards that south, to none. And that means the change is going to be to the right. That means the induced flux is going to be to the left. Again, the arrow's too big. But that tells me that the induced current goes up the front, down the back, and the induced current flows opposite what it did when I closed the switch. Okay? Now here's an example almost exactly like your tutorial homework. You have a ring that's not moving, so you can't use the relative motion idea. You have field lines that go through the ring to the right. And you have a magic knob that you can turn that will adjust the strength of the magnetic field. you turn the knob to make the field weaker. How would if I were to look at a weaker field, what would it look like? Fewer field lines, fewer field lines. So, if we look at those field lines, I got lots of them going through the loop to the right when the field is strong. I have fewer going to the right through the loop when it's weak. The change is what I have to add to that long vector to get the short vector. The induced flux or induced field lines will fight that change, so they will be to the right. In order for that induced flux to be to the right, induced current has to go up the back and down the front by right-hand rule number 3. So it would go like that. Now, you can use this formal construction to figure it out, or you can just use common sense. I got 20 field lines going this way. Now I got 18. Now I got 16. Now I got, fight the change, people, fight the change. What are you going to do? Now I got 12. Now I got 10. Now I got 8. What are you going to do? You can send field lines. That's the only thing you can do. You're going to send them that way or that way. Yeah, the whole point is they're dying to the right. If I want to fix this, if I want to fight that, I got to send field lines to the right. Okay? Now, if I turn the knob the other way so that the B field increases, I'd go from 20 field lines to the right to 22 to 24 to 28. How would you fight that? Send them the other way. Now, let's see if you really understand what I just said. There are smart lights in Bozeman and a whole lot of dumb ones. When you drive up to a dumb light at 3 in the morning and it's red and you're tired, it stays red. And it stays red. And it stays red. What do?
Run it.
You wait because you're a law-abiding citizen. And you wish to goodness that it was a smart light. Because a smart light, you drive up at 3 in the morning, it knows you're there, it knows you're tired, and pow, it's green. And if you drive up onto a smart light and you look down at the pavement, you see that they have cut a rectangle into the pavement. They put something down there and they patched it up. What did they put down in the pavement there before they patched it up? Any ideas? What? It's just a wire. That's all it is. It's just a wire coil. And when you drive your car over that wire coil, you change the number of field lines that go through the coil. Now it turns out, let's say this is the wire coil. We would have a bigger one at a real stoplight, okay? Without a car, there's field lines going through that loop due to the Earth's magnetic field, which points towards Canada and down 70 degrees. But only a couple field lines are going to go down through that. It's a weak field. But when you drive your Toyota over that, what you're driving is a Toyota magnet. That Toyota has an iron engine. The iron of the engine has a net magnetic field that's lined up with the Earth's magnetic field, Canada and down. And so that means by driving your Toyota over that loop, you're changing the number of field lines down through the loop from 3 field lines to 53 field lines. Fight that change. Fight that change. What way does the current, induced current, flow in that loop? Clockwise or counterclockwise? Clockwise or counterclockwise? Okay. While you're voting, at University of Washington, they have a really nice parking garage that's right underneath the central part of campus. And the only people that can park there are faculty that commute and very, very rich students with very fancy cars. The rest of the students have to park in a lot that is down a huge hill. There's the lot with steps going down. Now, when you come in to that lot, there's a smart light set up that senses your car, opens a gate, and lets you go in. But to get out, there's no such smart light. There's a place where you can put 4 quarters and it will open up and let you out. So if you come all the way down this mountain and you don't have 4 quarters, you get to hike back up and get 4 quarters. Well, I went down at 4 in the morning with a sledgehammer. I just wanted to see whether it would work. And I snuck over there where the smart light loop was. I set my sledgehammer there and it went right up. Well, the next day I was talking about Lenz's law. That's why I've gone down there. And I told my students that that happened.
Oh.
Yeah, my wife told me not to, but I did. They came back with a very interesting story. They said that they were able to take the metal can lid from a trash can, the iron trash can, and used it as a frisbee. Instead of going out the out, they went out the in. They would open their door, fling this frisbee. As it went across the loop, it would open up the gate. And they were out. Okay. Now,
It's a law-abiding citizen you are, Greg.
I didn't do it. I was just telling them physics. My wife told me I'd still go to hell, so I probably will. The answer is counterclockwise. Now, think of it this way. I go from 3 field lines down to 53 down. I fight that change by sending induced field lines up. If the induced field lines are going up, the induced current has to go counterclockwise to do that. Counterclockwise. Okay? Now, I have one more treat for you. I have an iron core, soft iron. This is not a magnet. This is a magnet. This is not a magnet. This is a magnet. This is not a magnet. Now if I take, oh, there's my loop. If I take a copper loop, right now there are no field lines through that copper loop. By hitting this button, I turn this into a magnet and suddenly put a whole lot of field lines through this loop. That loop doesn't like change. Now these field lines spread out at the end of the bar magnet. If this doesn't like change and it didn't have any field lines through it to begin with, where can it go to fight the change? Up there. Now here's another way of thinking of it. If hitting this button turns this into a north pole, then suddenly I'm going from 0 field lines up to a lot of field lines up. The ring is going to fight that by putting induced field lines down. That's going to put a north pole against the north pole, and it's going to jump. Now, if I have an aluminum ring that's lighter, yeah. Now, what about this copper ring that has a slice cut through it? Nothing. Now, the battery is set up as I change the number of field lines through this loop. That's fixed. But if I could somehow make this a better conductor, less resistive, I would get a bigger current, a bigger induced current, and it would become a stronger bar magnet. And it would jump higher. Now, clearly, I need more space. Now listen carefully. When it gets to 320 below, you'll hear a crescendo, and then it will stop. Here it comes. Okay. I got it.
Oh, dude.
Now, if I warm this up, it's not going to jump as high. Okay, Yosef, stand up and catch it. But don't hold it. Catch and release. Okay, are we ready? Catch and release. Send it back. Thank you. Okay, folks, we'll pick this up on Friday.